I just have to also tip my hat to Quivira. This has been an amazing morning, and I know it's going to be an amazing afternoon, not because I'm up here, but an amazing afternoon and tomorrow. And you know, I've been at a number of conferences and meetings over the last 5 years during these tough economic times, and a lot of places are shrinking, a lot of groups are shrinking, a lot of conferences are shrinking, and this one is growing. This is the biggest meeting we've had here, and to do that in these tough economic times is amazing. And it's such a testament to the strength of this movement, to all of you in this audience who believe what's going on here is the way of the future. And I know it's only going to get stronger and bigger and better. And it's thanks to the Quivira staff, to all of you, and to everyone who's supporting this work. It's a movement, and it's happening, and it's growing, and it's the most important thing we could be doing. So I'm thrilled to be here, and thank you all for also being here. This is just a tremendous conference. So my job this afternoon is to add to what we'd learned and thought about and talked about this morning with regard to seeds and soil, and to add water to this picture. The challenge of feeding 9 billion people on this finite planet with finite water is a very, very tough one. And I'm hoping to talk a little bit about that this morning. But I want to say right off the bat that while it's going to be really, really tough, it is entirely doable, and it's in part because of all the work on the ground that's going on that we're hearing about this morning, that we're going to be continuing to hear about, because it's all about using this finite water more productively. And it involves seeds, and it involves soil, and it involves the sun, and it involves respecting the atmosphere and what it gives to us. And I hope to try to begin to tie some of these things together. It's not just a water problem, it's all these things connected. We've just come off of an amazing time, you know, the last 50 years where the green revolution brought about this amazing productivity and yield. But it was at a tremendous cost to water, to energy, to the climate, in terms of the use of chemicals, pesticides and fertilizers in the soil, a degradation of fertility. And so while we don't know what we would have done had we not gone down that route, we know we can't continue with that into the future, that it's got to be something very different. And the pieces of that different vision are all here in this room, and they're all coming together. So I want to take a quick look at why we have a problem in the first place. I mean, this is an incredibly water-wealthy planet. But as you can see here, of all the water on Earth, 97.5% of it is seawater. It's ocean water. It's too salty to drink. It's too salty to grow crops. Only about 2.5% of all the water on this amazingly water-wealthy Earth is fresh. And of all that fresh water, of that small 2.5%, the vast majority of that is tied up in ice caps and glaciers, or it's too deep underground for us to access. So the water we're talking about is less than 1%, much less than 1% of all the water on the planet that we're dealing with in terms of fresh and accessible to us. Now, I'm not going to try to bring you back to 4th grade, but try to keep this picture in mind as we think about water in this picture of feeding 9 billion. This is the basic water cycle, right? The global hydrologic cycle. And the thing I want to point out about it is that our primary water supply is not rivers, it's not lakes, it's not groundwater. It's rain, it's precipitation, it's rain and snow. That's the primary source of water on the planet. And how we manage the land, and increasingly how we manage the atmosphere, affects what that rain and snow does when it hits the earth, right? Rain does one of two things when it hits the earth. It runs off. We have the runoff term right over here. Or it evapotranspires back to the atmosphere, or it infiltrates the soil. And how we manage the land influences very directly which of those things happens. I think it was Luna Leopold, the son of Aldo Leopold. He was a very eminent hydrologist. He said, what did he say? He said, one of the best measures, the quality of our water is the best measure of how we live on the land. And so that connection of land and water is one of the things we'll be talking about and hearing, I think, more and more about. Now, we have a finite supply of water, and nature has dealt a very difficult hand to us when it comes to water. We have to grow crops where it's sunny. That means there's not always an abundance of water there. And it turns out that populations have often chosen to live where there's not an abundance of that renewable water. So if you look around the world today, we have a picture of increasing water stress around the world. This picture would have looked really different prior to the Green Revolution. If we looked at this picture of the world in 1950, there would have been very, very little red in this picture. What this is showing is simply the amount of renewable water relative to how much of that water we're using. So it's sort of a ratio of our water use today to the renewable water supply that's there. And the redder you get, the more stressed that area of the world is. Okay, so you can see that there's tremendous water stress, not surprisingly, in the western United States, North Africa, Asia as a continent, incredibly water stressed. We have about 60% of the world's people living in Asia, but only about 36% of the renewable fresh water in Asia. So even as a continent, very, very water stressed. And this picture is getting more red all the time because we're going in a direction of increasing water use against that finite supply. Okay, so the challenge is really, and you can see much of the western United States, including right here where we are today, is in that water stressed category. So what's happening? What's happening in these places? We see a lot of rivers running dry, for one. Ecosystems are in decline in most of these places. We can see the Colorado running dry before it reaches the sea. It's been doing this for some decades. Only in those very high water years, those El Nino years, do you get a pulse of water running through the Colorado out to the sea again. But most years it looks like this. Just down the road, I took this picture in August, just a couple months ago. A dry Rio Grande looked like this for much of the summer. The dry Murray in Australia, another river that's been heavily overtapped. So this increasingly is the picture we have in these water-stressed river basins that are overtapped and in some ecological decline. The other thing you find in almost all of these areas in red is increased reliance on groundwater. And this is sort of one of those out of sight, out of mind water problems, especially when it comes to agriculture. Here's a picture from the air of the high plains, where you can see the big center pivot irrigation systems outlined in circles there. And this is in the western part of Kansas, where you can see, very productive but highly water-intensive agriculture going on. And if you look around the world at many of the places that were outlined in red and add up the amount of groundwater that's used today, we find that the depletion of those aquifers, groundwater depletion, has roughly doubled since about 1960. We've gotten much better data on this from satellites as well as from modeling efforts than we had even 10 years ago. And so it's roughly doubled since about 1960. And if you add all these areas up, what you find is that the amount of food we're producing today, about 10% of it depends on the overpumping of groundwater. Right? So that's a bubble in the food economy. If you can think of it, we know bubbles pop, right? It's a bubble in the food economy. We can't continue to overpump groundwater forever. So even some of the food we're producing today is unsustainable from a water point of view. If we look around the world at irrigated land, just at the cropland that's getting irrigation water, 18% of cropland gets irrigation water, okay? But it gives us 40% of our food. But look how concentrated that irrigated land is. It's all the areas that are outlined in red. So the 4 top countries, India, China, Pakistan, the United States, 4 top irrigators, and you can find those 2 things happening extensively in all 4 of those countries. Rivers running dry, overtapping of groundwater, and one thing I didn't mention, salinization of soil. The overapplication of water is degrading the fertility of soil by adding salts to it. And so you find that the fertility of the land is declining as a result of adding all this irrigation water to the soil and not flushing it out. So we have this unsustainable nature of irrigated production that leads a lot of us to think as much as 10 to 15% of our current food supply today is at risk to some degree from these trends in water use. The other thing to think about here is that if 18% of our cropland is irrigated, it means that 82% relies on rainfall. And that's in some sense been sort of the forgotten stepchild of agriculture. We focus so much on, you think about the Green Revolution, what was it? It was the expansion of high-yielding seeds, fertilizers, and irrigation throughout much of Asia, Latin America, and little tiny bit of Africa, not much. But those three things pretty much as a package shipped out, intensifying production, but requiring vast amounts of water. And this is the picture we're sort of left with. The research and changes that have occurred in rain-fed lands so far much, much less than the attention and investment given to irrigated land. And I think that'll be an important theme. The other piece, of course, we have to deal with is this change in climate. If you think about climate change, most of the way in which we're going to experience climate change is through the water cycle. As you get a warmer atmosphere, which we already have as a result of the temperature rise, as you get a warmer atmosphere, that atmosphere is able to hold more moisture. A warmer atmosphere, as it expands, is able to hold more moisture. So we're expecting to get an intensified water cycle. It's already intensifying. And so we'll see things like more intense flooding, more intense droughts as a result of evaporation increasing. We're going to see changes in river flows as a result of changes in snow melt. How much precipitation falls as snow, and then when and how much of that snow melt occurs during the spring. We're already seeing this, where we have much more precipitation falling as rain rather than snow, and then that snow melt is occurring earlier in the spring, which leaves water in the summer much lower. This is already beginning to happen. Glacial melting that we're beginning to see in the Himalayas, which is a water supply for 2 billion people, the Tibetan Himalayan plateau. So this is an added aspect of the food challenge. About 4 years ago, a group of 7 hydrologists got together and wrote a very interesting paper in the journal Science, and it was called "Stationarity is Dead." And what they meant by that is this, that if you look at natural systems, including hydrologic systems, they are naturally very variable. There's natural variability within the system, but they vary within a known set of boundaries. You can think of it like an envelope. So yes, you're going to have droughts, and yes, you're going to have floods, but they're within some known boundary that's familiar to us, and we can plan on that when we build a dam, when we decide to divert and channelize a river, what have you. We can use those data from the past and know with some degree of confidence that we're going to stay within that boundary. What they're telling us is that's no longer true, that we've moved outside that familiar envelope. We're outside that boundary. So the flooding we're going to expect now is different from anything we've seen before. The droughts that we can expect now are more serious and deeper and longer perhaps than we've ever seen, at least in modern times. I shouldn't say than ever before, because we've seen some of these things in the distant past. But in terms of planning for the future, it's a new day. And so the experience of the past with regard to water is not going to be, the experience that we have in the future. And so these trends are complicating our thinking and our picture of how we're going to meet the food needs of 9 billion people, how we're going to find and secure the water to meet the food needs of 9 billion people. And these stresses are already beginning to appear. And one of the ways they're appearing is in the price of food. If you look at the recent history, this is going back to 1990, and just looking at this is a global index that's put out regularly by the United Nations Food and Agriculture Organization. And there's 2 graphs here. One is showing the real price, one is showing the nominal price. They both basically track each other, so you can look at either one. But notice what's happened is that since about 2002, we have an upward trend in the graph as a whole, and we've had a couple of quite severe spikes in food prices. And what's happening is the convergence of these things we've been talking about. Water stress in more and more places, droughts on top of that water stress, higher grain demand, both from population growth as well as from the increased demand for grain-fed meat in particular. The diversion of crops to biofuels. We're now sending 5% of our global cereal production, our global grain production, to biofuels. So that's adding to the price of food. And then the weather extremes that we've seen. You know, the heat wave that struck Russia 2 years ago wiped out 40% of the wheat harvest. The drought, of course, we've just experienced here in this past summer. The flooding of 1/5 of Pakistan 2 summers ago. The 8-year drought in Australia, followed by unbelievably epic flooding the next year. These kinds of weather extremes are creating this potential for spiking of food prices. Now, spiking of food prices and higher food prices can be good, right, for agriculture, can be good for farmers. You get more income from your crops. But from a societal perspective, it's very, very challenging. When you look at what happened around the world during that food spike in 2008, there were riots, there were protests, there were very difficult social times during that spike. We had food riots in 12 countries, from Haiti to Mauritania, around the world. Some people say the Arab Spring resulted in part because of this underlying tension over rising food prices. You know, we might experience a 1 or 2 or 3 cent increase in our bread prices, but in developing countries and poorer countries, those kinds of price increases result in 10 to 20% increases in the price of bread, basic staples of food. And so it causes enormous amount of social tension. We heard this morning about the military getting increasingly concerned about water security and food security. You know, I've been working on water for 30 years, and most of the media are concerned about water wars, the idea that we're going to go to war over water. I'm not so worried about that. What I'm worried about is this, the idea that we're going to have more tension over water for food and the price of food and how we're going to meet these needs. And so this is, I think, where the potential for social instability really arises, is how we're going to meet these needs and satisfy everyone's demands for food. So that's the question that we have to address. Given what's happening, how do we secure enough water to feed 9 billion and restore ecosystems to health without going deeper into water debt? What I'm talking about is that we're in a water debt situation in much of the world, but now we have to feed another 2 billion people. And on top of this, think about what we have today. I think it was mentioned by Molly this morning. We have already 850 million people in the world, nearly 1 in 10 that are malnourished, hungry right today. So even today, we're not meeting all the needs that we need to meet. And now we've got another couple billion come along with all these challenges. So how are we going to do this? And I don't have the answers. I think the answers are in this room. I know it. But I have some thoughts I'll throw out, and I'm interested in your reactions. Overall, I think if we have finite water and we have to meet this challenge, we're going to need something like a doubling of water productivity by 2025, when we're expected to have 8 billion, and by 2050, a quadrupling by 2050, when we're expected to have 9 billion. Yield, for sure, some, but I'm talking about benefit per unit water. How much benefit are we getting from every gallon of water that we access, that we use, that we in some way interact with in one form or another? That we're going to need to get double the benefit and then quadruple the benefit if we're going to have any chance, right, of meeting these needs. In terms of food, what does this mean? This is just a partial list of the things, and we've been talking about a lot of these already. So you'll see a lot of, I think, cross-fertilization of ideas, but these are, I think, some of the, at least among the top 10 probably, these 5. And I'm going to talk just a little bit about each of these. And each of these really could, it would be totally justified to spend a much longer time on each of these, but I want to just run through why I think each of these is part of the solution to meeting this challenge. The green revolution, as I mentioned, required an awful lot of irrigation, but it put very, very little emphasis on using that water efficiently. There's different numbers out there, but if you look at most large irrigation systems around the world, most of them are delivering water to crops at a very small percent. In other words, maybe 40% of the water that's accessed for irrigation is actually benefiting a crop. So there's a tremendous amount of improvement that could be made through using water more efficiently. Now, I'm not going to use equations here, but this is one equation that we should all have in the back of our minds, because everything we do, I shouldn't say everything, but almost every day, we're doing something that influences this equation. And this is the basic, the most fundamental hydrologic equation that there is. That when you have precipitation, it's going to divide between runoff, infiltration, and evapotranspiration. And so if you're a gardener, no matter what you're doing that involves the landscape, this equation in some way relates to what you're doing. Now, engineers and hydrologists often stop right here, but what's really important for us, and what I want to emphasize a little bit this afternoon, is the importance of separating out evaporation and transpiration. We're used to combining these terms because they're very difficult to measure separately, but in fact, there's a big difference between unproductive evaporation of water and productive transpiration of water. And much of what we heard this morning about intercropping and various other techniques of land techniques and cropping techniques involve turning unproductive evaporation into productive transpiration. And so looking at each of these categories, you've got precipitation coming down. We do need, of course, healthy runoff in the rivers, but we also need infiltration into the soil. We also need to begin turning more evaporation into productive transpiration in the soil. And this involves water management, but it also involves land management. And a lot of what we've been hearing about deals with this. So look, thinking about, for a second, improving irrigation efficiency. One of the methods that's been growing very rapidly now is drip irrigation, which does exactly this. It moves, it takes water that's applied to the land, reduces the evaporation losses, and makes sure that water that's going on the field goes directly to the roots of the plant. This is just a simple photo of drip irrigation. We've seen about a 6-fold increase in the area under drip irrigation in the last 20 years, so it's growing quite rapidly, but from a very, very small base. So globally, we're still at about 4% of global irrigated land under drip irrigation. But because you're delivering water directly to the roots, and actually subsurface irrigation is even more efficient in this regard, delivering water directly to the roots, you're reducing evaporation losses tremendously and making sure that the water you're applying is going to be transpired by the plant and used productively to increase yield. So where this has been used, when you convert from the more traditional flood or furrow irrigation to drip, you often get a doubling or tripling of water productivity because you're increasing yield, you're giving the plants water when they want it in the volumes that they want it, and you're reducing evaporative losses. So you're improving crop per drop tremendously in many instances. Here in the US, we've got about 7% of our irrigated land under drip. Most of that's in California, kind of the fruit and vegetable bowl, but also increasingly in other states as well. So there's still a long way we can go in terms of expanding drip irrigation. When I was at the Irrigation Conference a couple of years ago in Texas, I was talking with the managing director of Jain Irrigation, which is the second biggest irrigation company in the world, based in India. And he expects there to be $1 billion market just in India alone. And they're doing interesting work on drip irrigation of upland rice, you know, the staple for most of Asia. So we may be moving out of a time where it's just appropriate for fruits and vegetables and horticultural crops into even basic grains. We're seeing it used on corn even to some degree. So I think this has an awful lot of potential. We're also seeing, and this is very exciting to me, the expansion of very low-cost irrigation systems. I mentioned, 850 million people in the world are hungry today, right? The vast majority of them live on small farms. in sub-Saharan Africa and South Asia. And the reason they're hungry, even though they live on farms, is in part because they don't have a way to access water. In a sense, they were bypassed by the irrigation age that fueled the Green Revolution because those technologies were too expensive for them. So here's a drip irrigation system that costs probably on the order of $25. It's a simple system where you fill that drum in the back with water. Gravity basically sends water down through those tubes with small little holes in them. It's not nearly as efficient or as productive as the more expensive systems you find in California and Israel and so on, computerized and all that. But it allows a farmer like this to actually grow horticultural crops, vegetable crops, with some secure water supply, when that land was probably dry during the dry season. Couldn't grow anything without an ability to irrigate that land. And so this is extremely important. This is a little farm in Nepal. This is a photo by International Development Enterprises, which has helped to design and build and market these affordable technologies. $25 system that can irrigate about 400 plants with very little energy because it's all gravity fed from that little drum in the back. We're seeing solar-powered drip irrigation begin to move into some areas. This is more community-scale irrigation. This is a project in Benin in West Africa. A colleague of mine, Jennifer Burney, is working on this one. And tremendous opportunity where you basically have a lot of off-grid farmers. How are you going to get the energy to pump the water up? And here solar drip is beginning to make a difference for farmers there. One technology that I found perhaps most transformational in my experience in looking at this around the world is this simple technology called a treadle pump. This really kind of changed how I thought about irrigation, about agriculture, about food security. When I first came upon this pump, I was working on my irrigation book. It was 1999. This picture is more recent than this, but I traveled to Bangladesh in 1999 and passed by field upon field upon field that was dry. This was January. It was the dry season in Bangladesh. Nothing was happening in agriculture because there was no way to access water. And then suddenly, about an hour outside of Dhaka, Bangladesh, we came upon this area of fields that were green. People were out pumping just like this woman is here, these little machines called treadle pumps. They're a lot of work. You don't want to do it forever, but what it's doing is accessing shallow groundwater with an inexpensive pump. Cost $35 back then, still about the same. And it was a transformational technology because during the dry season, there was no way you could get water to irrigate these fields. And poor farmers, these are $1-a-day farmers, right? They're very, very risk averse. They have to be. So they're only going to invest in a technology if they're very certain that there's going to be a return on it in the first season. So the farmers we talked to here were irrigating not only basic grains like rice, but also vegetables that they could take to market. So it was a ticket out of poverty. It's a simple, simple technology, $35, that allowed access to water, allowed them to purchase better seeds and begin to get out of that poverty trap that they've been in. Now obviously you don't want to treadle this pump for hours and hours and hours for the rest of your life, but after you receive enough income, you can then begin to upgrade your farm. And it's been a ticket out of poverty for millions of people, especially in South Asia, but increasingly in sub-Saharan Africa. We heard a little bit this morning about intercropping. This is getting at the rain-fed picture, where you begin to grow crops together, and again, you're improving water productivity because you're making better use of that soil moisture, growing two crops at the same time. This is just one example of maize intercropped with cowpea, which is a very drought-tolerant, shade-tolerant crop that's a legume, so you're adding nitrogen to the soil, and it's a very popular crop to be intercropped in many developing countries. We've seen a number of examples about this morning. But it's another way, it's a land technique, it's a cropping pattern, but it's a way of increasing water productivity, sometimes quite dramatically. Again, I don't know nearly as much as many of you about managed grazing, but it's another way of improving water productivity. It's a way of getting more rainfall infiltrating into the soil. And so you're basically taking that rainfall that's coming down and making it into a productive resource. Managed grazing, you know the technique. You're basically not only getting more water in there, but also getting more carbon, right, out of the atmosphere, improving your yields of grasses. The research on this, I think, is still developing, but from what I've seen from what's been written in the literature, it seems that for every 1% increase in soil organic matter, that's an absolute increase, so going from 3 to 4% organic matter in the soil, or 4 to 5%, you can get somewhere between 18 to 24,000 extra gallons of water in the soil. That's plant available water. Your total water is going to increase even more than that, but an extra 18,000 to 24,000 gallons of water per acre in the soil from these kinds of techniques. I think there's an awful lot we can do with improving production, getting more crop per drop, getting more benefit per gallon from production systems. All these techniques and land and water management practices we're talking about. But I think we're also going to need something on the demand side of the equation, right? If we're going to be feeding 9 billion people, have enough water for that, enough water to restore ecosystems, not go into water debt, it seems to me we're also going to have to look at the demand side, and we've begun to talk about this a little bit this morning. If you look at the average American's water footprint, it's about 2,000 gallons a day. Only about 5% of that is actually coming out of your water tap at home. Most of it is in our diet. So if an average American consuming about 1,000 gallons a day just in our diet, right? Another third is through our energy use. Takes about 13 gallons of water for a gallon of gasoline. So energy is an important part of that footprint. And then, of course, our miscellaneous consumption and then our home water use. So beginning to think about more water-conscious consumption choices can make a big difference. And I think that's got to be part of the solution. Shifting from grain-fed to grass-fed beef. We have a pretty good number on the average for the world. The average hamburger for the world takes about 630 gallons of water to make. That's about a week's worth of water use at home, right, for one typical hamburger, right? But the kind of meat we had for lunch, the kind of meat that many of you are growing, very, very different picture. Maybe 10 to 50 gallons per hamburger, less than a glass of wine, less than a beer. And really, I think it's a net positive because of what we were just talking about. You're actually repairing the water cycle through managed grazing and grass-fed beef production. And so this is a dramatically different picture. If we begin to shift consumer choice from grain-fed to grass-fed beef, 35% of the grain production worldwide today goes to livestock. 35% of our corn, mostly corn and soy, 35% of what's grown, our grain that's grown, goes to feed livestock. So part of this sustainability picture, part of this regenerative picture we're coming to, feeding 9 billion, has got to involve using the cropland to feed people, using rangeland to raise meat, and stop using stop feeding grain to cattle and creating the hamburgers this way. So it's a big part of the solution, it seems to me. The other thing is thinking about the agricultural components in our everyday consumption. We've got here just a typical t-shirt. Guess how many gallons it takes to make a typical t-shirt? Anybody want to take a guess?
500.
Very close, actually, very close. 700. The average t-shirt, just a simple t-shirt, right? 700 gallons, that's because it takes a lot of water to grow cotton out in the field, right? This is not at the factory, it's out in the field. So this is water that's competing, this is water that's being used to grow cotton that's competing for water needed for other things. So just think about one example. If the top billion of us, right, the top billion consumers decided to purchase just 2 fewer cotton shirts in a year, I don't know how many cotton shirts we typically purchase, but let's just say we didn't purchase 2 in this year. And 1 billion of us did that. The top billion, that's enough water saved to feed nearly 5 million people, right? So simple consumption changes, simple decisions about how we consume and what we consume can be an important part of this picture. I think I've used up most of my time. I'm gonna stop there and just repeat that I think we can meet this challenge. It feels to me sometimes working on this for 30 years pretty daunting when I think about the growth that's coming, but I feel particularly energized being in this room and hearing about the solutions that you're all working on. The water picture is a daunting one, but I really do believe we have enough water. It's how we use it, it's how we share it with ourselves, among ourselves, and with the natural environment. And I think we can get there. So I think we have time for a couple of questions, so I'd like to stop. And if you have any questions, please do ask. And I thank you very much for your attention.
This is a rather indelicate question, but it's been really bothering me lately, knowing what we're facing with water, that we in this country and in other developed countries actually put potable, high-quality drinking water in our toilets and then use them for an unclean purpose. Is there any movement or thought being given to changing our cultural perception that we really need to be in clean water?
It's a great question, and I think it's a great prelude to our next speaker to some degree. But we are. I mean, I think the use of gray water in our homes for uses that don't require potable water, that's beginning to increase. Some cities actually now have 2 different sets of pipes coming into your home. One is bringing in, non-potable, but water you can use for gardening, for flushing toilets, and those kinds of uses. And then another set of pipes bringing in potable water. Composting toilets are beginning, but slowly, to come. The one thing with our water use in general, if you think about most of the water use in your home, very little of that is consumed, right? So you flush the toilet, it either goes through a septic system or goes into a wastewater treatment system. It goes somewhere, usually back to the environment. Now, in some cases, it just gets sent out to sea, and it's, for all intents and purposes, gone. But if we manage it right, we can use that again. I still think you're absolutely right. It's silly to be, collecting, treating, and delivering this potable water just to be flushed away. But in general, that is water we can, use again. And we've gotten more efficient about it. When I was a kid, it took 6 gallons at least of water to flush the toilet. Now the average is, if you go and buy a new toilet, it has to be, by law, 1.6 or less. So we've gotten much more efficient about it. But I agree, we can do this better. And we're flushing, nutrients down along with the water. So it's a crazy situation. Yes?
I was so glad to hear you separate the evaporation part from the transpiration part of evapotranspiration, because an argument that we've been having in Colorado about how much of that is actually saved from consumption. And I'd like to know if there's some research you could provide me with that measures exactly the difference in those 2 types of evaporation and transportation. In other words, if you switch from sprinkler irrigation to underground drip irrigation, how much percentage of water do you actually save in the evaporation part of that equation?
Yeah, there has been research done on that, and I'd be happy to give you some of those sources. It's not a lot, because it's very difficult to measure them separately, but there have been some studies done that show substantial savings, and I'd be happy to give you those references. Yes?
Groundwater, looking across the globe, have you seen regions that have actively engaged the issue of gaining groundwater levels back, and are they starting to have success?
Yeah, there are some areas that are starting to have success. In India, for example, just to cite one example, there's been tremendous problem of groundwater depletion. India is more dependent on groundwater than any other country, and they've had substantial problems with groundwater depletion. So they're starting to actively try to manage the depletion, for one. So you'll find villages throughout India that now get together, as a village and decide on setting a cap on how much water they can pump, because they realize this is their future. If they deplete their groundwater, they have no crop production into the future. So they've gotten together as a village, and it's voluntary. It's interesting what education and data can do if you get together and decide that this resource needs to be protected for the future. And so they're basically capping it and then figuring out a cropping pattern and a water budget that allows everyone to remain productive but stay within that cap. And it's the only sort of community managed groundwater situation I'm familiar with, but it's beginning to spread now throughout India. Closer to home, we have the High Plains Water District in Lubbock. In January, decided to do something unusual for Texas, where groundwater is basically considered to be, owned by the landowner above it, and it's been sort of a little bit hard to manage for that reason. They have a rule of capture where you can basically pump as much groundwater as you want from beneath your land. But they have established management districts in Texas because they're aware that this is a resource that in some fashion has to be managed. So the High Plains Water District now has what they call a 50-50 goal, where the Ogallala is like a fossil aquifer. It's like pumping oil, especially in that southern area. So what they've decided is we want to make sure we have at least 50% of our groundwater left in 50 years. So they have a 50-50 goal there now, where they're trying to plan the depletion so that at least in 50 years they have at least 50% of their water left. So they've capped groundwater pumping. It's so controversial they've delayed the implementation of it to 2014. It was supposed to go into effect this year, but it's not. But it's the kind of thing that's necessary, and it doesn't change the ownership. Farmers still own the groundwater, but to make sure that you have a resource into the future to establish some way to manage the depletion of it. So yeah, here and there we're definitely seeing some attention to groundwater, but it's still, largely out of sight, out of mind, and that's a concern. Yes, sir. Okay, one more. Yes, sir. You toss it, either one, whatever. Yeah.
Mine's related. So you kind of just answered sort of the first part of my question, which was about, I guess, maybe a Jevons paradox situation with water extraction. And for those of you who may or may not be familiar, Stanley Jevons was a British economist who talked about rates of coal extraction and sort of when the efficiency of the steam engine went from 1% to 2%. That was a monstrously large jump, and then people were afraid that increased rates of efficiency of use lead to increased rates of extraction. And I mean, given right the danger of aquifer depletion, is not something to worry about. And also, could you go back to the equation real quick, or but if you take the partial derivatives of precipitation and say you split up the evaporation and the transpiration, and you have changes in rates of transpiration for precipitation, how can you sort of holistically speaking, how can you expect to predict sort of the complex impact of increased efficiency of transpiration on all of the other aspects of that equation?
Boy, I wish I'd gone to the question over here. That's a great question. It's just a very complicated question. You have two different questions. Thank you very much for the question. A couple different things. One is, I think you raise a very, very important point, which is that increasing efficiency of anything doesn't secure the resource, right? It just means you're gonna exploit it more efficiently. So the missing piece of the equation in water are these caps that we're talking about. The idea that if we're going to save water for the future, for future generations, then you do have to make sure you keep your use of water, your exploitation of water within some sustainable limit. So, looking at groundwater recharge and discharge, and making sure that if you're exploiting groundwater, you're not depleting the reserve and you're not harming groundwater-dependent ecosystems, wetlands in particular, that are around. And we haven't done that in a lot of cases, in most cases. So the efficiency is a way of making better use of the water we are extracting, but you've got to accompany that with some cap that acknowledges that we want to protect ecosystems, we want to protect groundwater for the future, and that's often the missing piece. And I'll answer your other question if I can, maybe afterwards. I don't want to take up too much more time from Lisa. So thank you all very, very much.